Hello everyone, today we are going to start chapter 3, equilibrium of a particle. Whenever we are talking about equilibrium, that means that the summation of forces would be zero. Technically we are using second law of Newton. Second law of Newton indicates that summation of forces would be equal to m mass times acceleration. If there is no acceleration, that means that there is equilibrium, then summation of forces would be zero. Because we are dealing with Cartesian coordinates, so we decompose our force components into x, y, and z. If you are only dealing with two-dimensional problems, then you only need to write summation of forces in x and y equal to 0. The other important word that we are using here is particle. Particle is based on an assumption that our object does not have any dimension. Our object will have mass, but not any dimension. When we use the term rigid body later in this course, that means that we are not neglecting the object's dimension. The first step to solve any equilibrium problem is free body diagram. You always need to draw free body diagram. That's how engineers communicate to each other. Whenever students come to me ask for guidance on their projects, I always ask them to show me their free body diagram because that's how we communicate. So I'm going to show you the steps in drawing a good free body diagram by an example. So in this example, we are going to draw a free body diagram of a box on a rough inclined surface. Whenever we use the term rough, that means that we have friction. If we use the word smooth, that means that the friction can be neglected. The first step is in drawing free body diagram is to remove all supports and isolate the particle from its surrounding. So for this case, removing the supports would be pretty easy. It's just the inclined surface, and we have isolated our particle from its surrounding. Now the next step is showing all the forces acting on the particle. If I look at here, I know I have the force of mass, or the weight of the particle is mg. Then I have the normal force, N, and I have the friction force because it's on the rough inclined surface. And since the box is tending to go down the hill, therefore the friction force would be going upward. And the third step is labeling all the known and unknown force magnitudes and directions on the diagram. So if we know the mass, we can find the weight. Let's say the weight is 10 pounds, and then the angle here would be theta, would be the same angle as here, because those two lines are perpendicular to one another. This is the incline, and also I have the weight is perpendicular to this line, and the normal force is perpendicular to this line. So if these two are perpendicular and these two are perpendicular, therefore the angle between the two are going to be the same. We use this concept many times in this course. So this is a complete free body diagram of our box on an inclined surface. Well, let's look at more free body diagram examples. Here is a disc on an inclined surface. We want to draw the free body diagram. We do not have any friction here, so you don't see any frictional force. We have the tension, we have the weight, and we have the normal force. And the angle between normal force and perpendicular line is 30 degrees, or between the weight, based on the same thing that we talked earlier. So there are three forces acting on our disc on an inclined surface. Let's look at this crane that's holding a box. So the box is held by a rope. That rope has a tension, and then we have the weight. If you want to write the summation of forces and write the equilibrium, that would be the summation of forces in y direction would be 0. That gives us the conclusion that T is equals to the weight. So here we have a plate that is supported by two ropes. If I want to draw the free body diagram here, I have the two tensions and also the weight. The weight here is 5 kilograms. So times G 9.81 will give me the weight if I have the mass. Here a little bit more complex exercise. We want to draw a free body diagram of steel bar. So I want you to pause the video here and draw the free body diagram yourself, and then compare it with the solution to see if you have drawn it completely. We want to draw the free body diagram of this steel ball on this inclined surface. So here is the solution. You can compare it with what you have drawn. You can see this is a steel ball. I have separated from its surrounding. That's the first step in drawing free body diagram. The second step is to draw all the forces, and then the magnitudes and the direction. So I have the weight. I have the tension here because it's supported by C. This rope is gonna apply a tension force. And then a normal force here because it's in contact with two inclined surfaces, so it has two normal forces. And the angle between the two normal forces are 30 degrees, the same angle as the inclined surface. So we have 4 loads applied on our steel bar. One component that we use in free body diagram and in equilibrium problems is the pulley system. Pulley system does not change the magnitude of the force and only changes the direction. So here in this problem, because we are talking about the same rope, the tension here and the tension here would be the same. This is based on the assumption that there would be no friction force at the pulley. If there is a friction force, then the tension in the rope would be different. Let's look at an example that I have a pulley system that is hanging from the ceiling, and I'm going to pull up a box with a weight of 10 pounds. If there is friction force, this tension has to overcome this 10 pounds and also the friction force that is present here. So I have to apply a load more than 10 pounds. But in many problems, we are neglecting the friction. We call it frictionless pulley. In that case, the pulley does not change the tension. As long as it's the same rope, it's the same tension. So for example, for this problem, I'm dealing with the same rope here from A to B to C to D is the same rope. So the tension is the same in all sections of the rope. That simplifies the problem significantly because we have assumed that there is no friction. Whether that's a good assumption or a bad assumption, that's a judgment that we need to make in design. As an engineer, we tend to simplify equations to make them solvable, to make them straightforward. But always we need to indicate the validity of that assumption. Here is another example, but we have multiple ropes. So be careful here. I cannot say the tension in this rope, let's call it TA, would be the same as here. You see, these two are not the same because we are not talking about the same rope system. The other component that we have in equilibrium problem is spring. Spring force is proportional to its deformation. So I have a spring force Fs is proportional to deformation, that I'm going to call it S. And the proportional limit is K, which is spring constant. As an engineer, do we want high or low spring constants? Well, the answer is that it depends. It depends on the application. And the spring force is applied at the opposite direction of displacement. So if I'm trying to stretch this spring in this direction, the spring force is acting in the opposite direction. And S is the deformation, is the final length minus the original length, which here we show it by L naught. And what is the unit of spring constant? I can get the unit based on the equation. If I'm in SI system, I have Newton, and then this would be dimension meter. If I'm in British system, that would be pound over foot. Okay, that would be it for this lecture.